Hello everyone, I am Saurav Chakravarti and I will be presenting the paper on estimating the size of unions of sets in streaming models. So this is a joint work with Kuldeep Mill and Vinod Chandran. So here is the problem. So we are given a stream of sets S1 to Sm where the sets Si come from the universe omega, and we have been given two parameters epsilon and delta. And the goal is to estimate the size of the union of the sets. That is, with probability at least 1 minus delta, we have to output an estimate which is more than 1 minus epsilon times the size of the union and less than 1 plus epsilon times the size of the union. So, a special case of this problem is when the size of all these sets are 1. In this case, the problem boils down to the problem of finding the number of distinct elements in a string. Now, this problem has been very well studied in literature. So, in some sense, we are solving a generalization of the distinct element problem. Now, how are these sets accessed? When a set S comes, we are allowed the following three operations. We can know the size of the set, or we can sample uniformly from the set, or for any element x we can check if x is in the set or not. Any set system that allows us to make these above operations using something like order of log omega number of time and space complexity is called Delphic. So what's the setup? So we have a set of sets coming in a stream. When a set arrives, it is stored in a temporal memory. The set is then accessed using the set of operations, the three set of operations, and some information is stored in the workspace. Then the set disappears and the next set arrives. Finally, based on whatever we have in the workspace, we are supposed to output the estimate of the size of the union of the sets. Our goal is to optimize two concepts, namely the space complexity. Here we want to minimize the amount of space required in the workspace. Note that we don't include the space required in the temporary memory in the space complexity. Similarly, we have this update time complexity, where this is the time required to run the various operations on the set. So, in other words, this is the amount of time for which this a particular set is stored in the temporary memory. Now, this framework of finding the union of this of a stream of sets where the sets are Delphic is actually a pretty strong generalization of many problems that are well studied in literature. Here are three such examples, and we will be focusing on only the Cleese measure problem in this presentation. So, in the Cleese measure problem, the goal is to find the union of a set of parallel rectangles in d-dimensional space. So, in other words, the omega is delta to the power d, and each set is an axis parallel rectangle in r to the d, and our goal is to estimate the size of the union of the sets. Now, the first question to ask is that, is this set system Delphic? Now, it is not too hard to see that indeed it is. That is, you can do all the three operations in order of log omega number of steps. Now, this problem has been pretty well studied in the literature, and quite a number of papers has been written on this problem for special cases of d equals to 2 or d equals to 3 and so on. But for general d, it was a big open problem whether this Cleese measure problem can be done in space and update time complexity O tilde poly in d. So, in this paper, we proved that given any stream of Delphic sets S1 to Sm and parameters epsilon and delta, there is a very simple algorithm that estimates the size of the union of the sets, and the update time complexity is O tilde log square m 1 by epsilon square log omega, and space complexity is log m 1 by epsilon square log omega. Now, we should point out here that if the goal was just to optimize the space complexity and not worry about update time complexity, in that case this basically becomes the same as finding the number of distinct elements in a stream, or which is also known as the F0 estimation problem. And from the work of Kane, Nelson and Woodruff, we know the optimum space complexity for this problem is 1 over epsilon square log omega. So, our problem becomes interesting only because we want to also upper bound the update time complexity. As a implication of our result, we do get a polynomial in D algorithm for the Cleage measure problem. So, thus solving the long-standing open problem in this field. Our algorithm also has pretty interesting implications in the problem of counting the number of solutions in DNF and coverage estimation problems, but we will not be talking about these implications in this presentation. Instead, with whatever short time I have, I will be trying to present you the actual algorithm. The most beautiful part of our theorem is that our algorithm is actually very simple. So, before I present the actual algorithm, let me quickly go over what is the main idea of our algorithm. So, our algorithm is somewhat of a sample based algorithm. At any point of time, say after k elements in this stream, that is sets S1 to Sk has been seen, we want to store a random subset B of the union of S1 to Sk such that three criteria are satisfied. The first criteria is that every element in the union is in B independently with probability P. Second criteria is that this probability P should be small enough so that the amount of things stored or the size of the set P is not too large, and hence we don't incur a lot of space complexity. And thirdly, we want that the P is not too small. In fact, it should be at least as big as 1 by the size of the union. Now, if these three criteria are satisfied, then it is not hard to see that the size of the sample B by P is a good estimate for the union. The main question is, how do we sample from these sets so that these three criteria remain satisfied? Now, for the criteria number 1, we first make a very simple observation, namely union of S1 to Sk is nothing but a disjoint union of Sk and union of S1 to Sk minus 1 minus Sk. Now, this very simple observation helps us to design an algorithm so that criteria 1 is satisfied. For the criteria 2, the main idea is that the probability P with which we sample doesn't remain the same throughout the algorithm. In fact, as the algorithm proceeds, the P keeps on going down continuously, and every time the P goes down, we have to do some kind of a resampling of the set P to ensure that criteria 1 is satisfied. And criteria 3 actually follows from some standard concentration lemmas. Now, with all this said, let me jump into the algorithm. So, the algorithm starts with the probability P, which is pretty high and has a threshold value which is an upper bound on the size of the number of samples we will be keeping at any point of time. Now, when the set Si arrives, the first thing we do is that for every element in this set B, if S is in Si, we remove them from B, and then every element of the set Si is picked with probability P and added to B. So, this helps us to satisfy this criteria 1 that every element is sampled independently with probability P. For criteria number 2, so that we don't have the size of B growing too much As soon as the size of B crosses a threshold, we update the P or reduce the P to P by 2. And once we reduce the P by 2, we throw away each of the elements in B with probability half. So this is the resampling that we do, which helps us to kind of ensure that criteria 1 is still satisfied when we reduce P. And finally, we output size of B by P. The correctness of the algorithm is not too hard to prove, and that's what the beauty of this algorithm is, the simplicity of this particular sample based algorithm. For future work, some obvious questions can be asked. For example, is the log m required, or namely whether the complexity has to be dependent on m. Similarly, can we weaken the conditions of Delphic set? For example, is it necessary to know the size of the Delphic sets exactly, or can we do it even if we have an estimate of the size of the Delphic sets? And thirdly, since our algorithm is actually a sample based algorithm, it might be possible to design more practically implementable algorithms for some well studied streaming problems like the estimation of the number of distinct number problem. Thank you.